In this video, we will introduce a microscopic interpretation of the entropy. So let's say that you drop 100 coins on the floor. You can describe this in two different ways. First, you can say that you have 1/2 heads and 1/2 tails. This is a macroscopic description. But another way to describe the state could be to say coin number 1 is a head, coin number 2 is a tail, coin number 3 is a tail, and so on and so forth. And this would be a microscopic description. Now, 100 coins is a lot. So let's do an example if we have only 4 coins. A possible macroscopic state could be 4 heads, and it would correspond to 1 microscopic state. But if you have another macroscopic state, that would be 3 heads and 1 tail, then there are 4 possible microscopic states. Then if the macroscopic state is 2 heads and 2 tails, we have 6 possible microscopic states. And if the macroscopic state is 1 head and 3 tails, we have again 4 possible macroscopic states. And finally, the last possible macroscopic state is to have 4 tails, and in this case, there is only 1 microscopic state. And so you see that in general, 1 macroscopic state can correspond to many microscopic states. And you see that the macroscopic state that is the most likely is the one with 2 heads and 2 tails, and this is because it has the largest number of microscopic states. So if we take a quantity that represents the number of microscopic states for a given macroscopic state, this quantity will tend to be maximum and it will tend to increase. And so this quantity is entropy, and it is related to the number of microscopic states by the relation that S is equal to Kb ln of omega. So in this relation, Kb is the Boltzmann constant, which is equal to 1.38 times 10 to the power minus 23 joules per Kelvin. And omega is the number of microscopic states for a given macroscopic state. So this relation was found by Ludwig Boltzmann, and it is written at the top of his gravestone where he was buried in Vienna. So let's come back to the example of the free expansion. If you don't remember this example, before continuing this video, check again the video on entropy where we first introduced this example. So in the initial state, we have a certain number of microstates. So let's say we call this omega 1. The first thing to realize is that omega 1 is huge, right? There is no way we're going to count the number of microstates here. We have an infinite number of possible positions and an infinite number of possible velocities for each molecules in the box. And then after the expansion, we have a certain number of microstates omega 2. Again, this number is huge, but how does omega 2 compares to omega 1? If we had only 1 molecule, we have 2 times more positions for this molecule because we doubled the volume. And so we have 2 times more microstates. But if we have 2 molecules, then we have 4 times more positions. They can be both on the left. The first one can be on the left and the second one on the right, or the first one can be on the right and the second one can be on the left, or both of the molecules can be on the right. So you see that we have 4 times more positions compared to having both molecules on the left side. And we can continue like this, and if we have n molecules, then we have 2 to the power n more microscopic states. And so in the end, you see that omega 2 is equal to 2 exponent n times omega 1. So let's continue. We can calculate the change of entropy delta S. It is equal to the final entropy minus the initial entropy, so S2 minus S1. And that is equal to Kb ln of omega 2 minus Kb ln of omega 1. And so using the properties of the logarithm, you can write kb ln of omega 2 over omega 1. And since omega 2 is 2 exponent n times omega 1, then the entropy change is equal to kb ln of 2 exponent n. And again, you can use the properties of the logarithm to write that the entropy change is n kb ln of 2. Now, since kb is equal to the gas constant R over the Avogadro number, then n times kb is equal to nr, where lowercase n is the number of moles. And so the entropy change is equal to nr ln of 2. And now you see that this is the same relation as what we found in the video on entropy. So using S equal kb ln of omega is equivalent to our previous relation. Now, this definition of entropy is essentially based on a statistical effect. The system evolves in the direction that is the most probable. In fact, it is not forbidden to have all the molecules go back on the left side, but it is so much less probable that in reality it never happens. So the second law is in fact a statistics law. This is the first time that you learn a physical law that is actually based on probability.